Hi everyone, so this video is going to be about some machine learning basics and in particular data and feature engineering. So the idea here really is to get started on some basic machine learning. Now this video uses Python capabilities. So basically you need to cover the Python basics before actually covering this video, otherwise you won't know how to proceed. So I invite you to go back to Python basics if you haven't done so already and complete the lecture that's there before moving on to this. So now this is about data and feature engineering. And why am I telling you about data and feature engineering within the context of machine learning? So data and feature engineering is a huge part of the machine learning pipeline. Okay, so what it serves to do is to do the following. You take some raw data from whichever source has given you that data, and you want to make it into something that's palatable to your model. And this involves two different steps. So one is about the data pre-processing aspect. So how do you go from raw data with potentially mistakes in it, problems with it, to prepared data? And once you have prepared data, we will go through what we call feature engineering, which involves getting then engineered features. And then once you have this setup done, you can go through the model and then get the insights you want from that model. But what's important to do at this point in time is first go through this process of going from raw data to a data set that can be used for the model. Now, data pre-processing, I can't emphasize enough how important this is for the actual machine learning pipeline. So this quote has been doing the rounds in the data science world. So data scientists spend 80% of their time cleaning a data set and only 20% of their time actually running the model and analyzing it. So that tells you how important this is as a starting point. So there are many, many techniques for data pre-processing and feature engineering. In fact, there are whole books about these techniques. So for most of them, you would need a technical Python knowledge above the scope of what is covered in a business school typically, and certainly in business foundations. So for example, how to deal with, words, right? Natural language processing. So this is not at all what I'm aiming to cover over the course of this week. So we're going to focus here on the main issues, give some workarounds, and then I'll tell you how to use Python to deal with these issues. So bear in mind, though, that this list is far from exhaustive. To be able to talk about data pre-processing, you need to know what a data frame looks like. So just as a reminder, so a data frame, which is the type you use within the pandas structure, remember, of your Python notebooks. So a data frame looks like this. So here we have on the columns what we call the features. So they're the characteristics of each observation. So the observations here are, for example, your different customers, for example, your different plants, right? So they're different data points that you have. And for each data point that you have features that characterize them. So in the rows, you have what we call the observations. And in the columns, we have what you call the features. And the features are what define your observations. So this is always presented like this, columns being features and rows being observations. And within the features, you have two different types of features. So what we call the numerical values, so the features are numerical, and the categorical values, which are words. Okay, so these are two examples of categorical features, and this is an example of a numerical feature. So take a minute now to just pause this video and open the data pre-processing notebook. Once you're done, unpause me and we continue. So data pre-processing. So the first step you want to do in any pre-processing routine is do what I call data cleansing. So this is really not about trying to flag down, issues with the distribution of the data or anything like that. It's really about removing things that are clearly typos or some kind of mistake that's occurred. So a dataset may have any of the following issues: values that are not in the right format. So for example, you're expecting a number, you're getting a word. So that's clearly a typo. Invalid values. So anything that has to do with, you have negative values for a variable that can only be positive. Say for example, price, you have in there something that's negative, clearly a typo as well. Duplicate observations. So this is the case where someone has just inputted twice the same thing. You can just delete one of them. Row records that are basically empty. If you have a full observation that has nothing in it, then what's the point of keeping it there? And then another thing that you can remove is columns that have basically the same value for every single row. Those columns are useless. They don't explain any of the variability in the data set, so you can remove them. We're going to be working with a running example. So if you open your notebook, you'll see that this is the example we're working with, the iris data set. So what is it about? So the iris dataset is about three different types of irises. So one of them is setosa. And essentially you have in this dataset many different irises that have been measured. So for their sepal length, so that's a part of the iris, and for their petal length and width. So you have 5 different features, okay, in this dataset. And only one of them is categorical, the species. So let's start off with how to detect corrupt or invalid values in a data set. So to do that, it really depends on what kind of numerical of features you have. So if you have numerical features, you would typically use a histogram and check out the output. Again, I'm not thinking about the distribution. I don't care about the distribution of the data. I'm just checking to see if there are values there that seem completely crazy. It will also help identify entries which are not meant to be, which are not numerical. Because then the histogram won't run. So if you get an error message when you're trying to use the histogram, there may be in your data set values that are supposed to be numerical but are not. So take a look at the histogram, and do the values seem reasonable and not completely outlandish, then you're good to go. For categorical values, you can use the function .unique to get all the possible values taken on by your variable, and then you can check if they seem reasonable, and if they are, you can move forward. So open your data preprocessing notebook here and try doing this, then come back to this video. So this is what you should be typing in, right? To get a look at to get a look at whether these values are invalid or not. So you can use Seaborn, which is a package in Python, to plot. So sns.displot plots a histogram. And then you just need to input the column that you're interested, the feature that you're interested in looking at. And this you do by calling the dataset irisd, and in parentheses, the petal length. That's the feature you're interested in looking at. KD equals false. Here's just telling me that I don't want an approximating line to the histogram. So if you remove it and take a look at the difference, you'll see that the difference is some kind of approximation of the distribution, which we may not want to use. So here, if I take a look at the petal length, for example, seems good to me, between 1 and 7. That seems like reasonable values. I'm not looking here at this big gap or anything. I'm not interested in that. Just looking at whether these end values make sense. For this category species, once again, I call irisd species. So I'm looking at this particular feature, the species feature, and I'm taking a look at the unique values that come up within this category. And there are 3 of them: setosa, versicolor, and virginica, which are 3 different types of irises. So far, so good. So if they're not, so if you do have issues with either the histogram or the kind of values you're getting for your categorical values, you need to either drop the corresponding row or change the problematic value. So how to detect and delete duplicate rows. This is also something that we want to do. So there's a Python function that's ready-made. So I encourage you to go to your exercise book and try it out. And then come back to this video. So the way it's done with the video, so the way it's done within Python is in the following way. So you can actually check whether there are any duplicates. And this is done by putting a dot here and applying this function duplicated to iris dataset. So irisd.duplicated checks whether each row of the dataset is a duplicate and returns true or false depending on whether it's a duplicate. So dupes here contains all the duplicates. If you look at dupes.any, it will return true if there's any value in dupes that is equal to true. So if there are any duplicates, this will return true. If there are none, then it will return false. In our case, it returns true. There are duplicates. And the way we can see the problematic row is by taking a look at irisd indexed by dupes, because that will outline the 1 row or the 2 rows or the 3 rows that are duplicates. In this case, it's row 142, which is a duplicate of another row. So you don't need to run this every time, right? This is simply done so you can yourself visualize what the duplicates are. If you're not interested in doing that, then very easily you can simply delete the duplicates in an automatic way using Python. So what you do here is, so here I'm just printing the shape of the data set to see that we're losing one row in between. So the way this is done is by doing irisd.shape. Okay, so we have the shape here. It's 150 by 5. We then drop the duplicates, and writing in place equals true here just means that we're replacing irisd by irisd where the duplicates have been dropped. And then that can be confirmed because if I type in print irisd shape, I'm getting 149 by 5. So we've lost an observation here between the two. Okay, now moving on to detecting and deleting rows that have empty cells. Once again, start doing it on your Python notebook and then take a look at the solution here. So this is the way that we can detect empty cells, is by using the function isNA.any. So isNA looks at whether there are any missing cells in your dataset. .any returns if there's any missing cell in your particular column. So here's sepal length false, sepal width false, petal length false, petal width false, species false. So there are no empty cells in my dataset. If there are any rows and columns with empty cells, then you can use the drop.drop.na to drop either the row or the column that contains these empty sets. So if you write here axis equals 0, you'll be dropping the row with the empty cell. If you write axis equals 1, you'll be dropping the column with the empty cell. How tells you how this is going to be done. So it depends on what you want. If one empty value is enough for you to drop that row or that column, then you should use how equals any. You should use all if all values must be empty for the column to be dropped or for the row to be dropped. An alternative here is a threshold. So you can define here a threshold, which is a number. So it's the number of empty cells you need, empty cells in that row or that column that you need for it to be dropped. So it can be 5, for example. Anything that has more than 5 empty cells, depending on if it's a row or a column, will be dropped. Okay, so that's the idea. Now, how do we detect and delete columns that contain the same value for all rows? Very easy to do. You just type in irisd.nUnique. And this essentially counts the number of unique values you have for each possible feature. So for example, here species, I only have 3 possible values. Now, if there was a 1 in this list, then this means that for that feature, every single observation has the same value. Then you would just go ahead and drop that particular column by using df.drop columns equal this column name. Okay, so for example, species here. All good? Moving on now to scaling and normalizing. So scaling and normalizing is an important part of preprocessing a data set. So scaling and normalizing are 2 different ways of making the data set be on scales that are comparable. So they make sure that your data is on scales that are comparable. Normalizing means that you put your data between 0 and 1. So you do an operation that makes your data be between 0 and 1. Scaling is an operation that ensures that the mean of your data is 0 and the standard deviation is 1. So I encourage you to open your notebooks and to take a look at the exercise that is on scaling and normalizing. So learn how to do scaling and normalizing to your data set. Then come back to this video. Okay, so the way to do scaling or normalizing is in the following way. So you import from this library, you import a routine called preprocessing that we're going to apply to this matrix here, this 3x3. So the way to do normalizing, so to put your data between 0 and 1, you're going to call the routine preprocessing.min-max-scaler. Okay, so this is kind of calling the function that you're going to use later on. And the way you're going to apply it to your data is by calling again this function you've defined, min-max scaler, and fitting and transforming the x that you have, so this. And then if you take a look at x min max, you'll get something that looks like this. As you can see, all the entries are between 0 and 1. Now for x scaled, because it's such a common way of pre-processing data, you have a ready-made function to do it. If you just type in preprocessing.scalex, then you get a scaled x here, so the data is centered and scaled. Okay? So this is scaling and normalizing. So when should you use it? It's only useful for certain machine learning algorithms. So it's useful for regressions, for example, and what we call principal component analysis. It's not very useful for example, tree algorithms. So if your algorithm takes features and multiplies them by numbers, then chances are scaling normalizing could improve it. Some use cases. So I'm going to give a couple here. It's not always the case that you need to scale and normalize. You need to think carefully about what this brings you. So some columns, for example, are orders of magnitude different. So if your column A has values around 1 and your column B has values around 10 billion, then it's probably worth your while to scale your columns, because otherwise column B is going to completely dominate your data set. If your algorithm is returning warning messages of the type poor condition number, then you also need to go ahead and scale and normalize your dataset. Sometimes it can also lead to the output you get from your algorithm being incomprehensible, so a lot of empty values and so on and so forth. That can be a warning sign that you need to be using scaling and normalizing. So it's very application dependent. Moving on now to another part of data preprocessing, which is about imputation. So data imputation. So recall our previous data frame, right? So this was our data frame with different features. And suppose we had an empty cell here. We were able to detect that this was an empty cell. So pause this video for a moment and think, what could be different ways of dealing with this empty cell? What are the pros and cons of your methods? How would this change if you were considering a missing observation in the feature 2 column? Would there be any difference? So any difference between numerical and categorical? I'll let you think about that, so pause this video and then come back to it once you have an answer to this question. If you thought about this question, let's take a look at what we could do with, for example, if a numerical value is missing. So one way to move forward is to delete the rows and columns where the values are missing. This is an easy technique and maybe not the best. Another way of doing this is to replace the value with maybe the mean, or the largest value, or the smallest value in that column, or maybe the median. That's another easy way to do it. You can find the observation that is closest to it in other observations. So you take a look at an observation that matches your current observation on other features and replace the value there by the value that you see in that other observation. You can generalize this and maybe find a couple of observations that are close to it and then randomly pick one of them. You can also run a regression on rows where all the data is present and infer from it the missing values. Or, even better, you can run a regression on rows where all the data is present and infer from it the missing values, then add noise to the missing values to create many different possible values for those missing rows. Now, how does this change if we're considering categorical variables? Okay, well, deleting the rows and columns where the values are missing is still an option. What you can do now, which is quite nice, is create a new category, which is missing values. That can help. That can make things easier. So this is something that you weren't able to do for numerical variables. You can replace the value with the value that appears the most or the least. You can find the observation that is closest to it within other observations, exactly like we did for numerical variables, and use the value that's there. Finally, you can find observations that are close to it in other observations, so the same kind of thing as before, and randomly pick one. And finally, you can run what we call a classification algorithm on these rows. That's the hardest option, the one that's the less trivial to run. So there's something that I would like to tell you about relating to data imputation. So it's all about what the pattern of missing values looks like in your data frame. So you see here, if I look at the pattern of the missing values in my data frame, it seems kind of at random, right? There's no particular pattern to the way your observations are missing. In that scenario, it's what we call missing completely at random. It's down to, for example, human error. There's nothing to read into the pattern of the missing entries. There's another option where you're missing at random, it's called. And so essentially here, the absent entries depend on another feature. So if I took a look at this data frame, and I have here age and mammography results, what would you see here? What would you think is the pattern behind these empty values? Yeah, it's the age, right? So the age dictates whether you have a mammography or not. So obviously if you're too young, you probably don't have one, which is why you have an empty value here. This is what we call missing at random. The pattern of the empty values depends on another feature. And then finally, we have missing not at random. And this is the most complicated situation to deal with. So here, for example, consider the following. You have weight, age, and diabetes as your column. Each row is a patient. Now, if you take a look at this, you'll see that here we have the weight that's missing. Now, it seems from the pattern, we can maybe link it to the diabetes diagnosis. So it might be here that this weight is missing because somebody's self-censored and didn't want to give their weight, maybe because it was too high, maybe because it was too low. But here, this is what we call missing not at random. The entries are absent due to their value or to a feature that's not been accounted for. So this creates differences. It's very easy to deal with missing completely at random or missing at random. In these two scenarios, for example, you get good results if you use regression or classification to replace these values. When you have missing not at random, it's much, much harder. And this is typically a scenario where you need to make sure that you're adding new features maybe, or that you're really trying to look into the reasons why that data is missing. So for all of this, I encourage you to see the sklearn.impute library in Python. Finally, outliers. So an outlier is an observation that doesn't fit into your data set. So this can be due to corrupt data, typos, or what we call real outliers. So I'm going to present here two different methods for detecting outliers, but then it's up to you to see whether they're actually true outliers, so outliers that are due to corrupt data and typos that you need to drop, or if they actually correspond to real data, and then maybe you need to analyze why they're there before dropping them. So there are two ways of doing this that we're going to cover. The third way is not something that we're going to cover, but I want you to be aware of. So the first one is via box plots, which is maybe the most typical one that you've seen. And then there's z-score charts. So here you're going to try and look at numbers above 3 or below -3. And then finally you have anomaly detection, which is an unsupervised learning technique, which we're not going to cover. So now take a look at your notebook. Try and do the exercise there that's related to outliers. And once you're done, you can come back to this video and keep going. Okay, so what you've normally done in your notebooks is the following. So you've drawn not only the box plot, right? So if you look at the box plot, these 2 points here are the outliers. They only concern the Setosa species. Likewise here, this was a z-score technique. So in the z-score chart, you ran it on the petal width for the Setosa species, right? And here in this array, you were able to flag one outlier here, the 3.39. So you can see, if you take a look at which observation this corresponds to, that essentially corresponds to the highest observation here that you see here. So overall, these are two different ways of identifying outliers, and then it would be up to you to decide what you do with these observations that you see here. Okay? Now let me tell you a little bit about feature engineering. So feature engineering is about changing around the features somewhat. And a particular scenario where you need to do feature engineering is when you need to change the type of a feature to another type. So when you need to go from numerical to categorical or vice versa. So the one we're going to see in most detail is how to go from categorical to numerical. Reason behind this is because some algorithms only accept one kind of input. For example, regression only accepts numerical input. So it's useful to know how to go from one type of data to another. So we're going to see here how to go from categorical to numerical. So we need to pause the video and think about the following. In these two data sets, which both contain categorical features, can you see a difference between the two sets? And how would you propose to make them numbers? So think about this for a little bit, come back with an answer. And once you're done thinking about this and having the answer, play this video again. Okay, so the difference between these two categories is in terms of ranking. So the first matrix here, the small, large, and medium, we know how to rank this, right? We know that small is smaller than medium, which is smaller than large. So we could, for example, assign values 1, 2, and 3 to these variables. Blue, green, and red don't have this property, so I can't rank them. So I don't want to be giving them values 1, 2, and 3. So I'm going to deal with these two scenarios very differently. So here, for example, I'm going to replace them by 1, 2, and 3. All good. Here, I'm not. I'm going to do what we call one-hot encoding, which involves having one feature for every single possible value that you have in this categorical feature. So I create one feature for blue, one feature for green, one feature for red. And this is how I read it. Observation 1 has value 1 here in the blue category because it actually corresponds to a blue sweater, for example. It has 0 in green and red. Well, because it's neither one nor the other, it's blue. So same thing for observations 2 and 3. Now, we're not completely done at this point. We need to make sure, because this data is redundant, right, you can get column red by just looking at column blue and green. So we need to drop one of the columns. So typically we drop either the first or the last one between the ones we've created. So we always drop a redundant column. So take a look at your notebook here and what can be done here to do this in Python. Once you're done, you can come back. So as you see, the way of doing this, right, of doing this transformation from here to here is via the pd.get_dummies function. So if you apply this to your dataset iris_d and you do drop first equals true, you're going to end up with something that looks like this. So in this case, it's going to transform the species column of your iris dataset, and it's going to transform that column into 2 columns now because we've dropped the third one. It can also be useful sometimes to go from numerical to categorical. So the idea here is that you use what we call bucketization or data binning. So instead of having many different numerical values, you aggregate them into different bins, and then you can name the bins. So this can be useful in many different examples where you actually don't need a lot of nuance in your values. So for example, think about the case where you're trying to determine the house prices of certain houses you have. So you may have the latitude and longitude of every single house. So in itself, a small difference in latitude and longitude probably won't impact the price of the house much. So you can typically bucket latitude and longitude measures together and maybe make them into different areas of your city, which would then impact the house price. So I'm not going to go into this and how you do this in Python, but I think it's good to be aware of this scenario. Now moving on to feature selection and what we call dimension reduction. So feature selection is a hugely important part of data science and machine learning. Now it's so very case specific that it's hard, honestly, to describe in one go. So I'm just going to tell you that feature selection is all about picking the right features out of the whole set of features that you have. Often just a subset suffices to really explain your model. So there are different ways of selecting features, but it's very case specific, as I was saying. It's very dependent on the business you're working in and so on and so forth. So here, this is really where your intuition comes into play. There are numerical methods, mathematical methods that support this way of thinking, but I'm not going to go into them here. I just want you to be aware of this notion. So that's feature selection. It's all about dropping some specific features. So dimension reduction, on the other hand, involves creating new features from the old ones. This can be done quite easily via PCA, Principal Component Analysis, in unsupervised learning. Again, out of the scope of this class, but this particular video, but I wanted to make you aware of that. So it's very different for supervised versus unsupervised learning. So in supervised learning, there's always a notion of right versus wrong, which is given by the labels that you have in supervised learning. So that's feature selection right there. That enables you to select the right kind of features for your problem. Unsupervised learning, on the other hand, has no right versus wrong. So dimension reduction here is based on keeping similar amounts of variance between 2 different data sets. So I'm not going to go more into detail about this. This is really something that needs to be practiced a lot to become good at. Finally, let me tell you a little bit about transforms and interactions. So sometimes it can be very useful when you have a particular feature to transform it. So in particular, it can be very useful to be able to take an exponential of it or a log of it. So you'll see that actually in the homework that you do with your group in session 3. So in session 3, this becomes an important thing to know how to do, and this is exactly what you're going to be doing. So transforming a feature just involves basically changing that feature around by either taking powers of it or dividing it by a constant or multiplying it by a constant or taking a logarithm of it. So this is what we call a feature transform. You have an example in the notebook to do. For feature interactions, this is basically adding or multiplying or dividing two features together. So it's mixing up features together to obtain a new feature. Again, this can be very useful. If, for example, you have height and length of something and the actual thing that's intervening in your model is more about the area, then this typically would be a good feature interaction to add to your model, the area, and to get rid of the height and the length. So again, there's an example in your notebook to do. I encourage you to take a good look at all these examples you've covered, and then tune back in to this video. Okay, so that was about data preprocessing and feature engineering. So it's the very first lecture on machine learning basics. So let me know if you require any more lectures on on machine learning. So this was the first one. I can very easily produce more. So just let me know if that's of interest to you.